let's go back to our tangent and cotangent functions now in a graphing context. We've talked about these before algebraically, but it's time to talk about what the graphs look like and the key points and features of those graphs. And you can see on this top picture right here, I've drawn the tangent parent function, okay? That's with no transformations on it, no stretches or shifts or anything. And in this bottom picture, I have the cotangent function, also the parent function with no transformations at all. So we're going to talk about these key points, and then I also want to mention domain and domain restrictions for each of these. The range is pretty easy. You can see these functions just head up towards infinity and they go down towards negative infinity. So the range for a tangent or cotangent will always be negative infinity to infinity. Okay, that's an easy one. The domain is not so easy because we just have to pay attention to a couple of restrictions. These asymptotes right here restrict our function. The function can exist everywhere except at those asymptotes. So all of these values between negative pi over 2 and pi over 2 are fine. And likewise between pi over 2 and the next one, which is 3 pi over 2. But not pi over 2 itself, or negative pi over 2. And the reason for that should be pretty clear if you go back to our good old unit circle and we think about this. Remember what tangent is. Tangent is just equal to sine divided by cosine. And where do domain restrictions come from? Those are cases where we try to divide something by 0, right? We cannot divide by 0. So where is the cosine going to be equal to 0? Well, if you remember your unit circle, you remember that this is cosine equals 0, 90 degrees, or pi over 2. And likewise, down here, 3 pi over 2, or 270 degrees. Those are your domain restrictions for tangent, where the tangent function becomes undefined. Now, likewise, we have some domain restrictions on cotangent. If you remember what cotangent is, it's the reciprocal of tangent. So that's cosine over sine. Now, where does sine equal 0? That's at 0 degrees and, 0 radians and pi radians, which you can see is a different set of asymptotes on the cotangent curve. See, there's 0 radians. Here's pi radians. So that's the domain aspect of these things. And if you wanted, you could even make a formula for domain because you're going to have an infinite number of these domain restrictions. Every time you hit a periodic repetition of the function, you're going to have another asymptote. So we can express that idea in a formula. So let's think, what are these domain restrictions? Well, if I wanted to make a list, maybe this would be the easiest way to come up with our formula. My list of domain restrictions is going to be pi over 2, 3 pi over 2, 5 pi over 2, and etc. Okay, on forever. And likewise, negative pi over 2, negative 3 pi over 2, etc. So to come up with a formula, what we really need is some way of saying pi over 2 times odd numbers. Okay, whether they're positive or negative odd numbers. And the way you say odd numbers in algebra is this. You say pi over 2 times 2n plus 1, where n is an integer. Okay, the algebraic way of saying n is an integer is n is a subset of the integer values. Okay, that's maybe TMI. I don't know. So we make this formula using n. And any n that you plug in, 0, 1, 2, go ahead, try it out. You're going to get an odd number in here. And if you wanted to describe all the asymptotes, that is how you would do it. Likewise, for cotangent, what are our asymptotes? Well, 0, pi, 2 pi, and likewise negative pi, negative 2 pi, and so on. This one's an easier formula. For this one, all you have to do is say, well, it's just n times pi, where n is any integer value. Okay? So that's a formulaic way to approach the asymptotes and the domain restrictions. Now, in this particular problem, if you're looking at it in your homework, it wants to know the key features and points. Well, look at what A is. A is this vertical asymptote right here. And the way you describe that is not with a coordinate, it's with an equation. X equals, I'm looking at the graph, and I see negative pi over 2. And likewise, if I look at point E over here, that's going to be x equals positive pi over 2. All right, so that's 2 parts of this. And then the rest we fill in as if they were our good old sine and cosine functions. We're looking for a coordinate point. That's the key point. So this one would be negative pi over 4, comma, negative 1. C, right in the middle of the tangent function, would be, that's just 0 on x and 0 on y. That's a nice one. And then the point D is pi over 4, comma 1. So that's the way you go about filling out this problem. Now, you'll see in this graph, I've drawn a little red dotted line in these graphing pictures. See, I'm trying to draw your attention to this graphing window. And that red box that I just outlined tells you just about everything you need to know about this tangent function. It tells us what the midline is, right? The midline cuts down the middle of the box right there. It tells you what the amplitude is, the height up and down of the box. Only in amplitude, it's not really good to talk about amplitude with tangent and cotangent functions, so we change that word to vertical scaling. Because amplitude describes how tall something is, and you can see this really has an infinite height up and down. So amplitude is not the right word. We say vertical scaling, but it means the same thing. And let's see, period, right? Period hasn't changed. That is the width of this box. Okay, so a lot of these features that we recognize from sine and cosine functions are going to be similar for a tangent function. It's just that we have to get used to a new idea of finding the phase shift and these asymptotes. And we'll get into that in future videos.